Welcome to Video 1 of the Diagnostic Assessments of Proportional Reasoning website. We have created a series of 4 videos to provide individuals who wish to use the assessments with the background on how they are designed to ensure scores are interpreted and used in ways that will scaffold students' understanding. The Diagnostic Assessments of Proportional Reasoning, DAPR, are designed to measure student-composed unit and multiplicative comparison conceptions in proportional reasoning situations. This video will review the scalar and functional relationships that exist in proportional situations. Subsequent videos will connect the scalar and functional relationships to students' composed unit and multiplicative comparison understanding. Following this short video, you will be asked a few questions regarding the content of the video before moving on to following videos. Thank you for joining us. Proportional reasoning is a student's ability to understand situations involving ratios, proportions, and rates. It extends beyond just looking at the relationship of equality between two ratios, or comparing the multiplicative relationship between two numbers. Note the definition of rates we are using from the NCTM Essential Understandings of Ratios, Proportions, and Proportional Reasoning. This definition of rate as a set of infinitely many equivalent ratios is different from many textbook definitions. Why is focusing on proportional reasoning important? Proportional reasoning is key to students' success in both math and science classes, but also benefits them in future careers. Most importantly, strengthening proportional reasoning skills impacts a student's ability to conceptually understand more complex and challenging topics. The relationships that exist in proportional reasoning situations are often categorized as either scalar relationship or a functional relationship. Problems involving these two relationships are typically equal in difficulty as long as the number sizes are similar. This graphic gives us a quick glance at the difference between scalar and functional relationships. Scalar relationships are based on the idea that we can scale ratios up or down to generate equivalent ratios. In this case, the scalar relationship involves the multiplicative relationship between the 6 and the 24, which is times 4. It also recognizes that each quantity in the $6 for 3 cookies ratio can be scaled up by a value of 4 to determine that 12 cookies would then cost $24. The functional relationship, however, focuses on the multiplicative comparison within the ratio. This functional relationship involves identifying one of the quantities in the ratio as the base quantity, and then determining the multiplicative relationship that the second quantity has to the initial base value. So if we treat the 3 cookies as the base value and the $6 as the second quantity, then we see that the cost is always 2 times the number of cookies. However, if we instead treat the cost as the base value, then the multiplicative comparison then changes, and the quantity of cookies is always half the cost. This graphic provides an iconic representation of the scalar relationship. In this image, in each rectangle, there are 2 purple squares for every 6 blue squares. The question asks, how many blue squares are there for 9 purple squares? In order to begin solving this problem, we begin with our original set of 2 purple squares. We would start by scaling up our quantity of purples. First we have 2, then we have 4, 6, 8. We have 4 sets, and then half of another set would give us 9 purple squares. But then we would need to continue this same scaling relationship to the blue squares, which initially began with 6, and then was scaled by the same factor of 4½ sets to give us the resulting 27 blue squares for the 9 purple squares. Although this graphic looks very similar, its purpose is to look at a different relationship between the values. Instead of scaling by thinking about how many groups of 2 it takes to equal 9, we instead focus on the multiplicative relationship between the 2 orange squares and the 6 blue squares. There are 3 times as many blue squares as there are orange squares in each set. Or conversely, we can think of the orange squares as representing 1/3 of the blue squares. This functional relationship can help us see then that if there are 9 oranges, we can use the multiplicative relationship of times 3 to determine then that there are 27 blue squares for 9 orange squares. In most proportional problems, students can make use of the scalar or functional relationship. The way task or assessment questions are phrased can often lead students to focus on using either the functional or scalar relationship. In the first problem, Hillary knows that cookies are 5 for $2. By asking the question, how much will it cost to buy 20 cookies, students are pressed to use the times 4 scalar relationship due to the ease of that number relationship compared to the times 2.5 for the functional relationship. In contrast, the second question asks, given the relationship of 4 burgers for $16, how many burgers can Thomas buy for $20? The difficulty of determining the multiplicative relationship between 16 and 20 presses students to look at the relationship between the 4 and the $16 and determine the functional relationship. As mentioned before, these types of problems are equivalent in difficulty with similar number sets, but by manipulating the number relationships, teachers can encourage students' flexible use of both scalar and functional relationships when creating practice and assessment contexts. You have now completed the Module 1 video. Please click on the link below to take the accompanying quiz. Following the quiz, be sure to view your quiz results. This is where you will be given the password characters needed to access the assessments. Be sure to write down password characters as you complete each module, and then proceed to the following modules.